IT enthusiast with a long-held experience in leading enterprise-scale projects across several industries. He has worked in the US and Europe as a senior project manager at OpenNebula, where he is responsible for the delivery of open-source cloud and edge technology solutions to meet quickly evolving business needs in the marketplace. It's the innovation and drive to bring new capabilities to market that makes his work most exciting. Edge computing is becoming increasingly popular because of its benefits in security, latency, and user experience. OpenNebula is a leading open-source IaaS platform to build elastic private clouds and manage data center virtualization, combining technologies like VMware vCenter, KVM, LXD system containers, and Firecracker micro VMs. OpenNebula is now developing an innovative open-source edge computing platform which will include a public catalog of public cloud and bare metal providers and their available global edge resources. This talk introduces OpenNebula's OneEdge R&D initiative and explains the project's journey from managing corporate data center infrastructures to its new features for serverless computing and distributed edge cloud deployments. Welcome, Michael.
Hello, everyone. I'm glad to be here today. I'm going to review some of the capabilities provided by OpenNebula, and in particular those related to creating cloud infrastructures with edge resources. I'm also going to dig into a few particular use cases related to the Internet of Things, as well as the integration of tools like Kubernetes in deploying dynamic infrastructure solutions. Okay, so just a quick intro. My name is Michael Abdou. I work at OpenNebula Systems as a project manager. So OpenNebula is an open source virtual data center and cloud management platform. And my job as a project manager is really focused on the development and release of that software. And at OpenNebula Systems, we're a company that has a dedicated focus on the evolving needs of our customers, our partners, and the users of OpenNebula. We're a single organization that's focused on taking the pulse of our users to develop a comprehensive roadmap, right, for delivering a leading cloud management software. We also provide enterprise support and services to organizations, and we've really been and remain a point of reference in the enterprise cloud industry. From a platform perspective, flexibility and simplicity have always been driving forces. With shared storage and networking resources, OpenNebula allows you to create essentially an enterprise cloud to service DevOps and development workloads alike. It supports virtualization technologies like KVM and VMware, as well as LXD system containers, and our upcoming software release within the next week or so is going to bring full support for Firecracker micro VMs for serverless environments. So on top of that, OpenNebula provides a simple and easy to use graphical user interface called Sunstone for both admins and end users. And it also allows you to easily exploit third-party tools like Kubernetes, Terraform, Ansible, and Docker. Here we like to say OpenNebula provides one cloud to rule them all. That's a sly reference to the Lord of the Rings, but also a keen reference to the fact that while OpenNebula takes its roots from the private cloud, it has vigorously evolved, right, in providing all the benefits of managing a private cloud while easily being able to integrate not only on-premises resources, but also hosted resources, edge resources that can be provided by public bare metal resource providers, or also to create hybrid clouds with public cloud providers like Amazon and Microsoft Azure. And this is what we're calling the enterprise cloud. This is a quick overview of the history of OpenNebula Systems and the OpenNebula open source project that we've been leading for over a decade now. Our work is really focused on user-driven delivery of cloud infrastructure solutions. There are over 5,000 active OpenNebula clouds running, with the largest one in production spanning 16 different data centers and including 300,000 different cores. If you look down below, you can see some of the users and customers of OpenNebula across many different industries. Not only is this a testament of the flexibility of OpenNebula, but it also helps to outline the fact that it is enterprise and production ready. Now I'm going to talk a bit about our One Edge initiative, which has been a work stream of ours focused on bringing cloud management capabilities to the edge. So for the past few years, we've seen the enormous shift towards being able to provide dramatically increased compute power with demands for highly reduced latency. The world of IoT, video gaming, and smart technology, they've all pushed us toward a paradigm where the centralized cloud is no longer a one-size-fits-all solution. And with One Edge, we've been focused on taking OpenNebula and developing innovative solutions to extend its flexibility and usability to distributed edge cloud environments. The One Edge project of ours has been granted exclusive funding by the European Union's Horizon 2020 Commission for Innovation. And it's the basis for the work that we're doing on the edge. So as I pointed out before, we've been moving rapidly toward a technology architecture that can support highly distributed computing power. Over history, over time, we've been moving and evolving toward the centralized cloud model, which has served us really well, with centralized managed resources, eliminating the need for individual organizations, right, to have their own discrete infrastructure. But with the requirements of our evolving technologies making real-time speed of thought response times a critical requirement, the shift is now making its way back to a distributed architecture. Data protection needs, right, are driving the need for more isolated and secure environments. And bare metal providers are stepping up all over the globe to provide resources for these distributed solutions. So the public cloud is definitely a driving force in the market. With more and more organizations, when assessing the prospect of implementing cloud solutions, they're making knee-jerk reactions to jump to the public cloud with organizations like Amazon and Microsoft. And yes, the dynamics of what they provide are drastically different from managing your own infrastructure, and they do definitely provide a great amount of benefits that organizations look to take advantage of. However, not everything the public cloud provides can be seen through these rose-colored glasses. When comparing these public cloud offerings to private cloud solutions, the public cloud is not necessarily always cheaper. A lot of it depends on the variability of workloads running on the system. Companies like Amazon promote that they can scale easier and cheaper. But not only does it depend on the variability, but there's also a threshold for the relation between scalability and cost. The public cloud is not always more efficient either. For applications that have bandwidth dependencies or which need to communicate regularly with other internal resources within an organization, right? On-premises typically takes the cake here. And centrally located public cloud resource providers don't offer the low latency benefits of the more globally widespread edge resource locations for apps that need to be geographically within geographical proximity to users. Public clouds do not provide the level of control and privacy provided by private clouds, obviously. With more and more data sovereignty requirements and regulations, as well as heightened value placed on data collection, storage, and processing, the public cloud is not typically one's best option. And one interesting dynamic that many organizations fail to take into account in the long run is the vendor lock-in that comes into play over time and commitment to public cloud offerings. Not only do providers like Amazon require large implementations to commit to minimum usage quotas that can result into huge investments. But having the flexibility and freedom to make future strategic technology decisions away from a certain vendor, that becomes almost impossible. All right, so the representative look at on-premises private clouds are generally defined by the benefits of first being able to run on bare metal infrastructure, providing performance benefits and increased flexibility. They also provide broadly isolated, private and secure environments. And they provide the flexibility and adaptability for one's organization's specific needs. However, there are costs, right? And one of them is the fixed costs, right, that are related to the infrastructure that an organization has to own. The amount of elasticity is reduced, right? Because you certainly have a static set of resources. You need to have data center and administrative teams to manage that data center. And it's really focused on, again, a centralized approach. So on the other side, you've got the public cloud perspective, right? And they offer separate benefits, right? So you essentially alleviate the need for managing your own resources. You're essentially paying for a pay-per-use pricing fee. Public clouds obviously offer the heightened elasticity, so they can respond to the demands and ebbs in one's demand. And you actually have an organization that can actually manage that service for you. However, as I pointed out before, public clouds come with a heightened sense of vendor lock-in, and they're not always as flexible in terms of being able to service all different types of applications. So what OpenNebula provides is essentially a private cloud base with flexible and comprehensive integration with public cloud providers. And this is what we call the elastic private cloud. You essentially have the flexibility to reap the benefits of public cloud resource providers while administering those resources from within a private OpenNebula cloud interface, just as you would manage and administer resources that are on premises. The elastic private cloud establishes its base from within the private cloud paradigm, right? But with the newly developed and innovative cloud disaggregation capabilities, along with the emergence of bare metal cloud infrastructure providers, and the increasing developments in automation, OpenNebula provides a new paradigm for the private cloud. With this elastic private cloud, you can take your private on-premises cloud, regardless of how many on-premises resources you have. It could actually be 0. And you can automatically and on demand deploy nodes with your own images on public bare metal resource providers around the globe in proximity to your specific user demands. If you look at the diagram here at the bottom, we are working on creating a mounting catalog of edge resource providers from which an OpenNebula cloud can plug into and utilize on demand. The OpenNebula cloud can include a mixture of resources, right, from on-premises, hosted, hybrid, any or all of them, all within a single OpenNebula instance. And up top, you see that you have the flexibility to run all of your applications independently on all of these resources. A key point here is that we're not here to compete with the Amazons and Microsofts of the public cloud world. We're essentially providing a dynamic administration layer that can sit on top of these providers and completely open up the flexibility and freedom to use these great resources while providing a whole slew of other benefits related to managing and controlling and navigating your private cloud solution, right? So OpenNebula provides complete backward compatibility and support for KVM and VMware hypervisors, as well as LXD containers and like I mentioned, Firecracker micro VMs. It is elastic and has on-demand provisioning capabilities, which provide organizations really the freedom to grow and shrink one's infrastructure at any point in time. Similarly, it provides the flexibility to deploy those resources on centralized cloud resource providers or at the edge or at edge locations around the world, right, depending on the workload needs. It is completely portable and compatible in being able to leverage essentially the growing ecosystem of providers. The resources, whether they're on premises or publicly provided, are dedicated and isolated, providing increased security. And you can benefit from the pay-per-use pricing structure, but without any vendor lock-in at all. So if one day you would like to use a different provider, there are no constraints, neither contractual or technological, that you need to consider. One key component on which we're placing heavy focus is in the development of a resource provider catalog. So with OpenNebula's flexibility in allowing organizations to build cloud infrastructures on widely diverse resources, companies can pick and choose resource providers. They should be able to pick amongst centralized cloud providers, edge cloud providers, or even access networks. And with continued development on API integrations with resource providers, users will be presented with a growing catalog of providers from which to simply click and choose, right, where they want to deploy images and manage specific needed resources. So we have many representative use cases to review which highlight the ease, flexibility, and speed in putting OpenNebula to work in real-life situations. The first one here outlines how to create and deploy the infrastructure required for a video game release. With the growth and popularity of interactive gaming and the rapidly advancing technologies, right, to provide a complete gaming experience, the importance of speed of thought response time has really become a key factor. You can just ask my kids and their friends who complain when they're playing Fortnite and there's a lag in the response time and their characters don't move with the fluidity that they innately expect. This is a very typical and valuable edge computing use case. Why? Because the user experience can be dramatically improved by bringing the computing power closer to the gamers. What we did here was to create an OpenNebula cloud and configured and deployed gaming servers for an interactive video game in 17 different edge locations around the world, across locations in the US, Europe, Asia, and Australia. And we created essentially a completely distributed cloud, all under 25 minutes. And OpenNebula's integrated provisioning capability makes it automatic and easy, in this case allowing gaming companies to be able to react to real-time demands to either grow or shrink the infrastructure as needed. A comparable use case is one that we carried out for media companies to handle over-the-top media distribution, which includes the streaming of videos and live events, which similarly require the ability to augment resources at certain points in time to meet a dramatic shift in users' demands. So on-premises infrastructures typically don't dynamically adapt to these highly variable demands, and they would require a huge investment on the infrastructure needed to meet those peaks in demand. And then what happens after those peak demands pass, and you have a huge amount of physical resources sitting idle. In this case, we show how media companies can build live, on-demand media workflows using OpenNebula. A broadcasting company can create a cloud infrastructure by selecting templates with the flexibility to choose the providers, geographical location, as well as lower-level attributes to meet their specific needs at any point in time. and they can review and manage those resources as needed through the OpenNebula cloud. Another use case involves the work of a long-held collaboration that we've been carrying out with Telefonica, a leading global telecom partner. And in this case, we've been looking to take advantage of providing edge resources by taking advantage of their central offices. So for telecom companies that have central offices that are really widely distributed geographically, they can offer a resource option with the possibility of reducing user latency to almost nothing. And OpenNebula's integration with being able to manage and deploy resources from telecom central offices, that provides another highly distributed option for creating and expanding one's cloud infrastructure. And lastly, we have a use case with the Internet of Things, right? In this case, utilizing AWS IoT Greengrass and extending Amazon Web Services capabilities to nodes on the edge. So in this case, we have a company that provides a monitoring as a service, and one which ultimately needs a largely distributed infrastructure to be able to provide performance metrics for their customers' websites from different locations around the world. The organization's architecture schema is essentially split into two parts, right? So one, which runs the general centralized services, right? And that stores the measured metrics, generates the graphs and the dashboards, all the BI capabilities, alerts the customers, and triggers custom recovery actions. Then we have the core distributed monitoring infrastructure, which are the probe capabilities, right? Those are responsible for measuring how each customer's site perform. And those are the services that benefit from being in very close proximity to the end target, really in order to eliminate the effects of latency on the monitoring and capturing the measurements. And this is where we provide the means to run custom AWS Lambda functions on these core devices. I want to dig into this IoT case just a bit more. So as I pointed out, OpenNebula provides the integrated capability of building an on-premises private cloud, one which allows you to deploy, administer, and manage your cloud infrastructure from an on-premises OpenNebula front end, while at the same time offering the flexibility to deploy on demand resources that are available on the edge, and which could be provided by public cloud providers. So in this case, we instantiated an OpenNebula cloud and then deployed bare metal resources from Packet. And using OpenNebula's one provision command, we deployed 15 different edge nodes, each at a different location around the globe, and configured them as KVM hypervisors with OpenNebula AWS IoT Greengrass appliances installed, right, which incorporate the AWS credentials. These nodes were built and deployed to carry out the core distributed monitoring services that I mentioned before, which use the Lambda functions. So now I'm going to show you a quick 6-minute video. It's pre-recorded of the actual use case deployment. It includes the configuration and deployment of the edge cloud as well as its simple cleanup. Today I'm going to deploy an AWS IoT Greengrass Edge Cloud infrastructure managed by OpenNebula on 15 locations worldwide and provided by Packet Bare Metal Hosting. I'll quickly review the infrastructure before we start. You can see there's nothing ready in OpenNebula, and Packet and AWS are all also pretty clean. So we'll move to the provisioning. We have a set of scripts which only ensure the parallel execution of OpenNebula one provision command. It imports the Greengrass image and triggers the code deployment. So when the scripts finish, the infrastructure is ready with a deployed application. Okay, for the demo, we've implemented a monitoring Lambda function which will be doing an ad hoc ping
on the requested target from each location. And in the red terminal, we're now starting a monitoring agent which controls them and displays the gathered data. Basically, it's a distributed ping command. We can quickly check now how the monitoring Lambda function looks like. It's pretty simple and straightforward. We only run a ping command and parse its output from the Python code. All right, we're deploying 15 physical hosts on packet bare metal hosting at 15 different locations. Each host is automatically configured as a KVM hypervisor, and the virtual machine with the Greengrass appliance by the OpenNebula started there. Then AWS deploys the monitoring Lambda function into each virtual machine. In the left terminal, you can see the list of the physical hosts dynamically created in OpenNebula and how they're switching from initial to a ready use state. And later, virtual machines will appear there as well. With the first virtual machines, we'll start getting monitoring data from their Lambda functions, so we can watch the red terminal. Now as we fast forward to the state when all locations are ready. So just hang on a few seconds. Okay, we're back to normal speed. We can see the deployment finished in just 23 minutes. The red terminal shows the latencies of the OpenNebula website measured from our new 15 locations with the monitoring Lambda function. Okay, we try again to check the example.com latencies. Okay, take a look at them there. Or we can check the google.com, which is performing really well from all locations. All right. Also, we have our own machine to check how site unreachability reflects in the output. So we try the IP of that machine. All right, it works. Now we reboot the machine. Okay, you can see the host becomes unreachable from all locations very quickly. Again, now we're going to review what we've deployed. In the OpenNebula, we have a set of new hypervisor hosts running on the packet, and Greengrass virtual machines are running there. The dashboard on packet shows all the deployed hosts. On AWS, you can see a set of groups created there for each monitoring location, dynamically by the automation inside the OpenNebula Greengrass appliance. All right. At the end, we clean up the infrastructure. We terminate the virtual machines and release the physical hosts. You can now watch as the cleanup finishes, but you'll see that it wraps up in just 27 seconds. So that's pretty much it. Thank you for watching.
I'm also going to quickly review another key use case. which is being able to use OpenNebula with Kubernetes on edge resources. So I have another short recorded demo of this use case, which reviews the provisioning of edge resources using OpenNebula, of then instantiating the Kubernetes services on edge nodes, and ultimately deploying the Agonis platform to run the gaming servers on Kubernetes. So here's this one. In this video, I want to show how gaming companies can deploy multiplayer game servers at the edge by using OpenNebula edge computing features along with Kubernetes. In particular, I'll show how to focus on provisioning and managing the infrastructure that can support a gaming company to build and deploy a multiplayer game by using the Agonis platform for multiplayer game servers and using the Kubernetes service along with edge computing features provided by OpenNebula. And then I'll follow up with a demo based on these tools. Agonis is an open source platform developed by Google in collaboration with Ubisoft on top of the distributed system platform Kubernetes. Agonis extends Kubernetes in such a way one can create, run, manage, and scale dedicated game servers within Kubernetes clusters using standard Kubernetes tooling and APIs. Agonis's main focus is online multiplayer fast-paced games, such as first-person shooter games and multiplayer online battle arena games. These are games that require dedicated low-latency game servers. And latency is very much a key concern, since the competitive real-time aspects of the games require quick responses from the server. That means that the connection from the player device to the game server should be the shortest possible in terms of latency. Higher latency, in turn, degrades the perceived game quality. In order to deploy Agonis's system, we need resources geographically close to the players, and this is where OpenNebula edge computing features play an important role for providing an automated solution through which the gaming companies can build their own light and agile edge computing environments, and they can provision the Kubernetes clusters on the edge nodes in close proximity to the gamers. All of this to satisfy the low latency requirements. So OpenNebula takes an opportunistic approach to its edge node provisioning model by taking advantage of already available resources that are offered by third-party bare metal resource providers. In this way, gaming companies, they have the ability to easily create their own edge environments and manage them with simplicity without having to provide or own those underlying resources at all. And once the edge physical nodes from existing bare metal cloud providers are provisioned, OpenNebula will allow to deploy in a software form the other infrastructure components that are needed on the edge, such as the software-defined networking, the virtual network functions, software-defined storage, and virtual machines or containers. By providing a marketplace with pre-built appliances, OpenNebula facilitates the deployment and management of applications that run on the edge, such as Kubernetes clusters. And the Kubernetes service appliance that is available in the OpenNebula marketplace, it allows you to bootstrap a fully functional Kubernetes cluster on the edge. All right, now let's get ready for the demo. So in the demo, what I'm going to do is provision edge physical nodes by using Mini1, which is an easy-to-use deployment tool, to build OpenNebula cloud-based environments. Then I'll deploy Kubernetes clusters by using the Market Appliance service on the edge physical nodes, and then I'll follow up by deploying the Agonis platform for provisioning Exonotic game servers, which is a first-person shooter game. Here we have the OpenNebula front end, without any other resources, that's been deployed on a packet host. By using Mini1, we're going to provision physical edge nodes from different facilities of the packet cloud provider. One resource is going to be deployed on an AMS1 location in Amsterdam, together with the configuration of virtual networks, image data store, and the Kubernetes service appliance from the edge marketplace. Another one's going to be deployed on SJC1, which is Silicon Valley in California. And the third one will be deployed on NRT1 in Tokyo, Japan. Okay, so for each of these locations, the Kubernetes service appliance from the marketplace will be imported for each data store. And right now, the deployment activities is set. It will probably take about 5 minutes to complete. Okay, so about 5 minutes has elapsed, right? And we've come back. You can see that the resources have been deployed and they're ready within the OpenNebula cloud environment. Now what we're going to do is instantiate the Kubernetes cluster in each location. For the AMS1 location, we instantiate a VM by using the template of the Kubernetes service imported by Mini1. For SJC1 and NRT1, we'll essentially do the same. Okay. Again, the Kubernetes instantiation, it'll take about 5 minutes or so. So we'll wait 5 minutes until the Kubernetes clusters are ready, and I'll return. Okay, the Kubernetes clusters are now ready in all 3 locations. Okay, we'll show the latency from each of the locations by pinging the VM public IPs. And ultimately, we select the facility with the lowest latency. In our case, it's the AMS1 in Amsterdam. So we'll connect with SSH to the Kubernetes cluster deployed on AMS1, and we're going to deploy the Agonist system and a game server. First, we create the namespace for the Agonist system. Then we deploy the Agonist platform by using kubectl. After we've deployed the Agonist platform, we can proceed to deploy a game server for the Exonatic game, which is a free first-person shooter game. We are going to use the game server YAML file that is available on Agonist GitHub repository. We'll check if the Agonist system is running by using kubectl, get pods in the Agonist system namespace. Then we can deploy the Exonatic game server. And here we'll have to wait about 5 more minutes until the game server is ready. Okay, so once the game server is ready, we can connect with the Exonatic client to the game server by using the public IP of the Kubernetes VM and use the port that's displayed by the kubectl get game server command. Okay. Entering the IP and port. All right. Now we can join the game that's been created on the Kubernetes cluster. Let's take a look. And here we go. All right, I really hope this was helpful. So now, if you're looking for more information about OpenNebula and you want to figure out where to start, here are some references to help. Again, OpenNebula is fully open source. It's available for downloading and putting it to direct use. We have Mini1, which is an available tool that we have allowing you to download and deploy a simple OpenNebula cloud in just a few minutes. Here's also a reference to our open source Edge Cloud datasheet for some high-level features and capabilities. And you also have the Open Cloud Reference Architecture white paper available for a deeper dive into best practices. Here you have some information about our organization, some of our local offices. And lastly, once again, here's a reference to, again, the European Union's Horizon 2020 Commission for Innovation, right, which is partially funding the work and advancements that we're making here. So, hope this was helpful. I want to thank you for joining.
Thank you, Michael. OpenNebula has a fascinating example of a multi-cloud implementation with edge computing. I'm sure we're going to have quite a few questions, and so we'll go ahead and take those over in the Q&A session so we can dive in a little bit deeper. Thank you.